Let's talk about graphing motion. Using a graph to show how different variables relate with each other can actually tell us quite a bit about motion. And we use two different types of graphs the most frequently. We use a position time graph and a velocity time graph. So for a position time graph, we're plotting the displacement on the y-axis and time on the x-axis. And the slope of that line tells you the instantaneous velocity. So let's look at an example. We have two different objects, and looking at these lines, we can tell a lot about their motion, even though there's no numbers on our axes. So we're not doing any calculations, but we can tell a lot about the motion anyway. So let's look at object A. When we look at this, you can see its position. It starts in the negative and then goes up to the positive. And we know on a position time graph, the slope of the line is the velocity. And the reason that is because, slope is rise over run. So rise over run would be position over time, which is velocity. So we know that the slope of this line is positive. We also know that it's constant. Because it's a straight line, the slope is the same everywhere. So it's positive and constant. Velocity, make sure we remember that. Object B, we can look at it and we can see that its slope, its velocity, is also positive and constant. But we can also tell that its slope is less than object A's because of the steepness of the line. So we know that while object B has a positive constant velocity, it has a positive constant velocity that is less than object A. Here's another example. We have three different objects in the still position time graphs. Let's look at object A, the red line. We can see its position doesn't change. Its y-axis value is the same the whole time. So its velocity is 0. For object B, we have a curvy line, and that means that its velocity changes throughout. You could calculate the instantaneous velocity at any point by calculating the slope at that point. But sometimes it's negative and sometimes it's positive. So we can't tell anything overall about the velocity other than the fact that it's changing. For object C in the yellow, we have a line that slopes downwards, which means that it has a negative but constant velocity because it is still a straight line. Any straight line at all, no matter which way it's pointed, means the velocity doesn't change. Velocity time graphs show how fast an object is moving. So we have velocity on the y-axis and time on the x-axis. For these graphs, the slope of the line is acceleration because the slope is rise over run, which is velocity over time. And that's how we calculate our acceleration. For these, the area under the curve is displacement. Now, if the line's actually curved, to calculate the area under it, we have to use calculus. So what we'll do is get the area under the curve where the line is straight, and it'll end up being some shape out of geometry that you can calculate the area of. So let's look at this example. And this graph looks a lot like one of the graphs we saw previously, but it's really important to look at what the axes are. This is velocity over time. So we're talking about these objects' motions. Object A, when this was a position time graph, object A wasn't moving. But this is a velocity time graph. So object A has a velocity that doesn't change. So that means that object A has in fact, we know it's a positive velocity that doesn't change. It has no acceleration and a positive velocity that doesn't change. Object B, the blue line, has a positive and constant acceleration because the slope would be positive and constant. And object C has a negative and constant acceleration. So even though these graphs can look really similar, it's very important that you take a look at the axes so you know if the slope tells you about the velocity or about the acceleration. And you can always figure it out by looking at them, even if you don't remember, because we calculate slope by rise over run. and we know that velocity over time is acceleration. Let's talk about displacement. Let's look at this example. We actually put some numbers on it this time. So first, what is the object's acceleration? Because the line is straight, we know that its acceleration is constant. So we can get it at any point and it will be the same value. So let's do it over here where there's not anything else written. So we do rise over run. Then we can read on our graph. We have to do a little estimation. So I'm going to say this is 16 and that's 20. So that means our rise is 4. Make sure you don't say that it's 20. And we go from 8 to 10 seconds. So divided by 2. So our acceleration is 2 meters per second squared. And we can tell our units by looking at the units the axes are measured in. So the next question asks us about how far the object travels. And this is our displacement. So in the first 5 seconds, we know that we can find the displacement by looking at the area under the curve. And again, I told you we weren't going to use actual curves because that involves calculus. But I've outlined it in red already. The area under the curve between 0 and 5 seconds is a triangle. And we should know that to find the area of a triangle, we say 1/2 base times height. Base. So we would do, for this one, we would do 1/2 times base, and it's 5 seconds, times height, which is 10 meters per second. And I'm adding the units this time just to show you that you get the appropriate units. So you can see that the seconds cancel out. And we have 1/2 times 5 times 10, which equals 25 meters. So in the first 5 seconds, the object travels 25 meters. There we go. Let's look at the last question. It says, how far does the object travel between 8 and 10 seconds? In order to make this a little bit easier, I'm going to clear off the writing so far. So we can draw these lines just to kind of show it to ourselves a little bit more easily. And I promised you that you would be able to solve these as simple shapes. So if you look at this, you can see that it is a triangle on top of a rectangle. And you should be able to find the area of both of these shapes. So let's do the triangle first. It's still 1/2 base times height. So we do 1/2 times, and our base here is from 8 to 10, so it's 2. And our height is from what we said was 16 to 20, so it's 4. So the area of our triangle is 4. But that's not all of it, 4 meters. We also know that's this area right here. We also need to find the area of this rectangle. And we know that the area of a rectangle is just length times width. So we can know that we're going to do 2 times 16. So 2 times 16 gives us 32 meters. So the entire area under the curve, the displacement for the object between 8 and 10 seconds, is 32 plus 4, so it is 36 meters.